Welcome to Engineering Scale Models. I'm your host, Jason, and I do models. How is everyone doing today? I am doing rather well. I have my granddaughter for a week, so we're gonna have good times with that. So content's gonna be a little light this week, guys, because I don't have a whole lot of time filming, plus school for my son. So we're going to get into this here. This is my code crack game that I'm using a rotary encoder for a input and clock signal for a shift register, but I'm using a different shift register now. So I am using the 74LS164, which is a serial 8-bit serial in parallel out. So it will take a serial in and it will immediately put that output to the output. So as before I talked about in this series of just messing around, that I was losing a bit of data. There was a hidden bit in there, so it was really 9 bits long, and there was this hidden bit that you had to figure it out. So I got rid of the 595 chip, the 74 HC595, and I swapped it for a 74LS74 or SN74LS164. And then I have my 74LS14, my inverter with Schmidt triggers to invert the active high signals to invert them to make them more like a clock pulse, and we'll take a look at that here in a little bit. So basically you have a inputting of a master code here with these dip switches, and this is the code you want to match. I made a custom loom for the rotary encoder, so it just plugs in like so. Just plugs in like that. And then let's turn this on. I'm using a power supply from Siglent SPD3303XE. If we turn this on, we see we have 1 bit of data in there. Let's see if that helps. Okay, that helps a little bit. You can see that. So if I go this way, I shifted in all zeros. Now, if I set a combinational code, say I wanted this pattern to appear on there, I would need to shift in like a 1, a 1, a 0, a 1, 0, 0, 1, 1, and then I match the pattern. Now, it's super easy for me because I understand that's how it works, but for a 12-year-old, it's a fun little game. But this isn't the final product. There's going to be more. I'm actually going to have some PCBs made of this. This is just, I know I could do this with Adreno and all this stuff, but this is to teach my son like what computers were like before we had microcontrollers and just logic based functions, and to do a project. So the next step, I had this semi working in the last video, but now I have it, flushed out with these little bar graph meters. I like how it's missing bits. We're gonna do something with like extra bits on the side that do various things later down the road. But now I want to talk about what do? You match the code. Whoopsie-doo, right? Well, the rotary encoder has a button on it. So you click the button and it does something. The button's not hooked up right now. The button will be hooked up in the future, and it'll be hooked up to this button up here. Let me turn off this side view camera. It'll be hooked up to this button here, which will pulse this clock system with this 555 timer. And it'll pulse this clock system through this LS161, which is a 4-bit binary counter. Disregard this mess over here that's getting ripped off the thing. It was supposed to be a timer, but we're going to add that later. So as you pulse through, you click the button, you can count up to 16. So my thought was, well, I have some LS 189s, which are 4-bit by 16 addresses of memory. So I have 2 of these, so I can have an 8-bit word in an address of 16, and this counts to 16 different addresses. So you have address 0 through 15, and this counts from 0 to 15. So as you click the button, you would get, this would be address 1, or level 1, this would be level 2, level 3, level 4, level 5, level 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then you're back to level 0. Excuse me. So that gets you through 15 levels of the game, and then we're going to add some form of timer that you have to match the code in the allotted time for all 15 levels. Now, I aware that I'm using RAM. This is SRAM, static RAM, and as soon as you cut power to the game, all your levels are going to be reset. That's fine. We're going to have a manual level setting system here to where we just set the address with these 4 dip switches here, and then we can set the level as we see fit. And then we can set whatever code we want in there. And that is just a trial run for this system to make sure that works. And then I'm not sure if we're going to stick with that for the time being and move to the comparator circuit, to where we have some comparator chips, which I just got in. Here are 2 different 8-bit magnitude comparators. This is a 74. I'm going to have to take them out of the package. But these are 8-bit comparators now. I have 4-bit comparators, but these are 8-bit comparators here. So this is a LS 682. So I've talked about bit comparators, the 4-bit comparators in my logic series, which I'm not sure if that video is going to come out before this video. I'll try to get it out before this video on there. So so you can see that. That's my fault, guys. Sorry about that. So basically, it would take the output of this and the output from the switches or the RAM or whatever setting the master code, and it would compare it to this, what you inputted, and then at a equal match, when the code matches 100%, it would send a high signal to a system to light up an LED to let you know you got the code right and that you can continue on to the next level. Whether or not we have that continue to the next level on its own, run it through a pulse circuit, because if I press this and hold this button up here, it stays on level 1 until it is pressed and held again. So it would change the level. If I had that output go to this system up here, it would change to level 2, and then when the code misses, it would go low, and then it wouldn't affect anything. And then when the code matches again, it would then go to level 3, and then it would move up through the system. So I got 2 different chips. I got this 74 LS682, which I'm telling you, LS series chips are coming harder and harder to come by. I don't remember what these are. I ordered these months ago from China. Jamico didn't have them. This is a 74 HC688, and I believe it's the same type of chip, but they were slightly different. I found these first and went ahead with the HC chips because I can mix the high level CMOS with the LS. I would prefer to do it with all LS, and then I was able to find 5 of these LS chips, which would be great for my LS series. But I was able to find the LS, so I'm going to try on both and see which one I like better. The data sheets are slightly different on that, and when we get to this chip in the logic series, or that part into the building of the circuit, I will go over the data sheets for these magnitude comparators. And if I can't get these to work, I have the 4-bit comparators that I can cascade together to get 8 bits, and I know that gives me an equals out. Let me just come over here real quick. This is probably gonna pull up in the wrong spot. Let me just go to ti.com and pull up the data sheet on this real quick. First, I want to show you the data sheet on the LS189, 74 LS189. First, I'm going to show you the data sheet on the SRAM. Really? They don't have a data sheet on the LS 189? Are you serious? Did I get that wrong? Yeah, 74 LS 189. Why is that not listed as a data sheet? Wow, Texas Instruments doesn't have a data sheet for that. That is strange. 74 LS 189 data sheet PDF. I talk as I type. It's a Fairchild. It's a Fairchild semiconductor. I hate some of these sites. They make you pay for. They make you pay for the data sheet. No, I'm not a robot. So the 64-bit random access memory from Fairchild Semiconductor. If it opens up this, oh, it's going to scan it for viruses. Look at that. So if I go over to, oh, can I do monitor 1 on here? Yes, like, no, that is definitely monitor 1. Oh, that's an issue. Okay, so let's do this here. Okay, well, that's an issue, so okay, well, that's a thing. So hopefully this works now. Monitor 1. This is the 64-bit, so it has the 4 address lines. It's got A0, A1, 2, and 3. That's your 4 address lines, which will be connected to these dip switches, and also this program counter. Then it has your 4 data lines. It's got 4 input data lines, and it has 4 output, and the output's inverted, so I will have to run them through an inverter. Random access memory this small and this old is an obsolete chip, so it really is, it's an obsolete chip, so finding a 8-bit 64, 8-bit 4 address random access memory is just, it's very difficult to find random access memory this small, and I will show you an example of what I'm talking about, because I mess around with random access memory, and I have some others here. I have some, this is 8K, so 8 kilobytes, I believe. Let me just pull this up on a different screen here. Let me do this. So this is 64 bits. So there we go. There we go. So this 169 or 189 is 64 bits. This is an SRAM that's 8K. So this is not even a K, and this is then I have 248 word by 8-bit. So that not who that is. It probably has 10 address lines, maybe. Let's see how many address lines that one would have. I think that might be my smallest one. So let's take example how many. So if you were going to do a code crack game, you could have 2048 levels. So let's do 2 times 2 times 2 times 2. So that's 64 it's 4 bits. No, 8 bits is 64. So 9 bits is 128. 8 bits is 256. So 9 bits is 512. So 10 bits. So it's 11 bits. Let's just make sure I did that right. 2 to the power of 11. Okay, well, I totally messed that up. Well, man, I'm having some issues here on this calculator. Yeah, so 11 bits. So it's going to have 11 address lines. I tell you, I have one of these TI Inspires CAS calculators that I do, system of equations on, but sometimes simple math is just so difficult on it. It's just, I can do the super complex problems so easily, like with variables, and it solves all the variables in like a couple quick, easy steps. But trying to do something to an exponent is like 20,000. I don't know. I don't do it that often, so so this has 11 address lines, and then I have that is, I believe, some more of. No, this is a. This one I don't have labeled what this one is. This one is HM6264 LP10. So this one may be. Does it have the same number of pins? No, this one is a 12-bit address register. 12 address locations. So I have. I was hoping to get one with 8 address lines. So, but like I said, I get the 64-bit, or this one is 8K, another 8K. I have a whole lot of SRAM. So, and then my other option for permanent memory, this video is getting longer than I anticipated, is to use an EEPROM. Now this is an Atmel chip. This is probably my smallest EEPROM, and it is massive. Let's undo that, and let me search this data sheet here. This is AT28 C648 C648. Okay, so here we go. Let's bring this up. So this is the Atmel. This is 64K. This is 8K times 8. So this is got 8 outputs. If we look at the chip here, it's got 13 address lines. So it will hold it. You know, you don't need, if I use this for a permanent memory and program, you know, my 16 levels in it and just use the first, you know, 15 addresses, 16 addresses, you know, I could have a permanent, you know, game on here. Or, you know, if I use something like this, I can expand this program counter to 8 bits long or 6 bits long, you know, just cascade another counter in there. And then, you know, you have the option of 256 levels. That would use a little bit more of the EEPROM. Now, getting an EEPROM that is this style, where the address lines are accessible other than I²C, this is basically the smallest EEPROM I can find. I have some other EEPROMs here. This one is a... oh, you know what? I'm a liar. This one is smaller. I thought that was my smallest one. So let me just search this one here. AT. Okay. Yeah, that's not going to give me the data sheet. There's the data sheet. Of course, it's in this. See, this is what I'm talking about. You can't doubt. I just want the data sheet. No, I don't want that temperature sensor. Okay, DigiKey should have the data sheet that I can access. So this is a 16K parallel. This one is not in the package that I'm interested in. What are we looking for? The PC package. So 16 kilo. There's the data sheet. Okay, so this is 16K, so 2K by 8. So this one has, let me zoom in on this. It's small to me too. It's on my smaller screen. So this has 11 address lines. So this has A0 through A10, and then 8 outputs. So this would be smaller. I could do a smaller, you know, I could use a smaller one. So that one is my smaller one. So this one is this one is 16K, so 2K by 8, and then I have this one is 256, Okay. Another 256. This one is a 2864. I believe that's what this is. Yeah, that's what that other chip is. That's another 2864. And then another 256. And then 28 C16s, dash 20s. So I have some more of those. Believe it or not, I use these EPROMs in projects like this when I need to. And, you know, you can write to them. You can use an Arduino to write to them, or you can sit there and you can program every address by hand. Which, you know, if we only have, you know, 256 combinations, you know, you spend an hour programming it, and it's not, you know, it's not that big of a deal. So, eventually, first we're going to start with this, you know, these 189s, 16, 4-bit, 4 address each, or 16 addresses, 4 bits each, for just to use this 4-bit program counter. Eventually we'll move up to the comparator system. So the comparator system is after the memory system works, and then the clicking the levels, and then we will implement the comparator system to increment the levels when the code is correct. Then after that, I will decide if I want to pull the RAM and use an EPROM, and, you know, I'll use the EPROM. I'll just use the first 4 address lines, keep it at 16 levels, and then, you know, eventually cascade another binary counter and use an EPROM to get 256 levels. And, you know, I want to implement some form of timer circuit. I set up another 555 over here that can be adjusted with this potentiometer to a varying amount of time, but it's not very accurate. So I'm going to come up with a system of, you know, what's a good amount of time, or a way that you can keep track of time with another 4-bit counter that goes through a BCD decoder to 7-segment display. So every minute that goes by, it counts forward, and it displays, like, you know, 1 minute, 2 minutes, and then 3 minutes, and then 4 minutes. And then the goal eventually would be to get through all 256 before the timer runs out in 9 minutes. That may be extremely too long, and then, you know, I could adjust it to each number is 30 seconds, and then, you know, before it counts to 9, you know, gets to 10, 0 to 9, you know, time runs out. And, you know, that's later down the road. We haven't thought that far ahead, but the basic system to where the comparator jumps through the levels and the 256 levels with an EPROM is the goal I want to get to now, and I'm going to make PCBs for that, and I'm going to have custom PCBs made at that point, and we're going to build this in actuality, and I'm going to get better bar graphs that don't have a different light right here. And I like having the 2 extra bits that aren't used. It's a little confusing. We can color them in with a black marker, but I'm going to stick with this system for a little bit, and I might do some trickery bits in here to where it randomly plugs in a number there to confuse you. So that is where we're at. This video lasted a lot longer than I have anticipated, but this is the detailed workings of what's going on with this Code Crack project. It's a project for me and my son. He is 12 years old, and it is interesting. It's teaching a lot of things about digital logic and transistor to transistor logic, and how RC circuits and, you know, eventually comparators and memory and volatile memory and, you know, ROM type memory and program counters and clock circuits. It's a very educational system here, and if you guys want to see more on this, and, you know, how to go about, you know, this is a very cheap and easy way to introduce kids to logic circuits, basic electronics. This is fundamentally basic electronics. You have LEDs, you have switches, you have simple inverter logic, you have simple shift register logic, you have a simple RC circuit with capacitors, resistors. You have simple 555 timer circuits. Everybody should know your 555 timer circuits. That is an astable, that is a monostable. A binary counter you should know, and it teaches you what binary numbers are. And this is a very simple project. It doesn't take more than a breadboard. You could probably even get away with a smaller breadboard. This is my testing breadboard. I have extra stuff that's not needed on here, but this is what I build on. I have another breadboard exactly like this that I do other my logic series on and stuff. So it's very nice, very simple. It's great. It's a great project to teach kids, how computers, not how they specifically started, but how, the fundamentals of computer with logic and things like that without overwhelming them, and then you can, later introduce OR gates and that comes in with the comparators and things like that. And you can, expose children to that in a fun game because, yeah, I cracked this super easy and it was no big deal, but to someone who doesn't understand logic and understand how a shift register works and understand how a rotary encoder works and how the clock signal and didn't build this unit, at first it's a little tricky, and if you put it to a time and pressure and things like that, you're going to make mistakes. If I try to do it quickly, I mess up and I miss it. Like I set up an 8-bit counter and I tried to just keep up with the counter. I slowed the clock down real slow and I tried to input the codes as they changed as fast as the clock was putting them out, and the clock was going real slow. I had like a second to a second and a half to input the code, and I couldn't keep up. It was too overwhelming. But I can put in a code. I can put in a code real quick. Well, I messed that one up. See, if I try to put it in real quick, I can put the codes in quickly, but if you put it on the pressure of you're going to run out of time and you got to clear it and you mess up once and you don't clear it fast enough, it can get tricky. So, and that's another option to where, it auto with a 555 timer in astable mode. You could slow your clock down and you could have it count through the program counter because it'll count through the program counter. And then you could slow it down and you could have it count through the levels, and you have to try to match as many levels as possible. And then you could set up the comparator circuit to pulse another 4-bit counter to see how many you got correct in the time frame. So you'd have another 4-bit counter, and the comparator would pulse it every time you got one right, and then it would just keep changing. So, that's another possible alternative gameplay mode on it. It might offer multiple gameplays on it on the final PCBs when I end up producing them and I share the file on my Patreon page. This will also be on a website coming up in the future in March of 2021. But this is, just a project that I don't put a lot of time into it. I put about 4 or 5 hours a week into it, just one day a week. I just spend one day. Normally, today's a Sunday. This won't go out on a Sunday, but today's a Sunday. It's kind of my lazy day, and I'll mess around with this. And other days, I'm working on, other projects that, generate money and things like that. This is just my project for me and my son to work on and have a good time. But I'm not going to make this video any longer, guys. You can check me out on these social media links. Keep updated. I don't really post a lot, but I need to get back into it. You can also support me on Patreon, where I'm going to be starting to upload the schematics as I get them, what I have so far, and different variations of it. It's going to be coming to Patreon soon.